we're playing with the idea of an antiderivative. So just a few examples of that and how it fits in with what's to come in calculus. So antiderivatives. So we can call this also a preview of calculus 2. Yeah. So preview of calculus 2 with antiderivatives. So just derivatives. We're getting pretty good at those now. So if we take something like x squared and we take the derivative of that, then we get 2x. If we take natural log of x and you take the derivative of that, we get 1 over x. So just a few we should remember. Sine of x gives us cosine of x. And we've accumulated a huge list of these derivative shortcuts here that we've just memorized, so we don't have to apply that definition all the time. Now, just like 6 divided by 2 equals 3, we also know that 3 times 2 is equal to 6. So we have this inverse operation. So we can go backwards. If we know a derivative, we can go this direction and say, hey, if I have the function 2x, its antiderivative, where it came from derivative-wise, is x squared. So this moving the other way is the idea of an antiderivative. And hopefully you guys get used to the fact that pretty much everything we do one direction in math, we try to figure out how to do it backwards, right? We learn to add and then subtract, multiply and then divide. We learn about powers, we learn about roots, exponents versus logarithms, sine and cosine versus arc sine, arc cosine. So we in mathematics, we look to invert everything. Things that move in one direction, we often need to look back to see where they came from. So that's this antiderivative idea. Let's see, antiderivative, there we go. Ah. Same here, sine, go the other way. Somebody gives us cosine, asks what's the antiderivative, we would say sine. Now, again, we've looked at lots of functions. So let's take, for example, the sine of x plus 5. If we take its derivative, we get just the cosine of x. Now, looking at that backwards is kind of interesting. The antiderivative of the cosine of x is also the sine of x plus 5. So because we have this idea that a derivative with respect to x of some constant is equal to 0, we lose track of information when we take a derivative. And so antiderivatives are not unique. Because of that idea that the rate of change of a constant function is 0. So the cosine of x actually has many antiderivatives, as do pretty much any other function. So antiderivatives for the cosine of x include just the sine of x, but also the sine of x plus 2, or the sine of x minus pi, pretty much any constant we want to combine here. So in general, given any function, its antiderivative will be some other function, like in this case the sine of x, but it could be plus absolutely any constant. That constant could be plus or minus, so we just put a plus there, so that could be a negative number. So this, for example, could be plus negative pi. So antiderivatives aren't unique. But based on our derivative idea, we can come up with a starting candidate for an antiderivative for a function. Then we would need more information about the function to figure out what the constant is. So for example, if I wanted to find an antiderivative for cosine of x, so the antiderivative for cosine of x is some function of x, and let's say I also know that f of x is equal to 0 is equal to 2. So I know a point on the function I'm looking for. So in general, an antiderivative for cosine would be the sine of x plus c. And I know, so this is my new f of x, I know that if I plug in 0 into that, I should get the answer of 2. So f of 0 would be the sine of 0 plus whatever c is, and I know that the result has to be 2, right? If I'm given that information, I can narrow down which of the many antiderivatives I really want. Well, what is the sine of 0? The sine of 0 is 0, so c would have to be 2. And the value over here, that 2, that's not always the value of c. It just kind of depends on the situation, what it's going to end up being. So in this case, I could say, all right, starting with the cosine of x as the derivative of some function, and the original function had the point 0, 2, then I can say that that antiderivative has to be the sine of x plus 2. Right? So I can figure out the missing constant. So the only way to figure out the missing constant is to be given some other information about the function, in particular, a point. All right, so we'll come back playing with antiderivatives in a second. So next, I want to connect this to the idea that we looked at in the beginning of the quarter. So first, we've been playing with derivatives. And a derivative gives us what's called the rate of change function. The derivative solves the rate of change problem for any curve. The other big problem in calculus is the accumulation or area problem. And we call that problem ultimately an integral. And the integral finds the area under the curve. And it turns out there's a connection between the two of them. So let's look at an example. Consider the function y equals 2x. So let's, I didn't place that very well. Scoot you over a little. Should be a little better. There we go. So 1, 2, 3, let's say 4, 5, 6, 7, 8 over there. The other way, I think I'll count 2, 4, 6, 8, 10, 12, 14, 16. And again, I'm going to look at, let's call it g of x equals 2x. So that, starting at the origin, has a slope of 2 over 1. So up 2 over 1, up 2 over 1. Right? So this would be my graph. So for example, that graph should have the point up here. 8 times 2 is 16. So I just changed the scale to make it easier to graph here. Next thing I want to consider is the area underneath this. So if I pick some x value, like x equals 4, then I want to know what's the area under the curve and above the x-axis. I want to know what that area is right there. Well, it's just a triangle, right? So I know that the area of a triangle is equal to 1/2 times the base times the height. So in this case, I get 1/2 times a base of 4 with a height of 8 that's going to give me an area of 16. And that 8 right there, according to this curve, if the base is the x value, then the height is always twice the x value. So if I pick any old x value over here, and I just say, hey, let's use a different color, this right here is just some x value called x, then this triangle would have a base of x and a height up to there of 2x to find that area right there. And so the formula for that area would just be 1/2 times the base, x, times the height, 2x. Cleaning that up a little bit, I get the area is always x squared. Interesting thing is the derivative of x squared, right? Derivative with respect to x of x squared is 2x. So reversing that, the antiderivative of 2x is x squared, or at least an antiderivative. The antiderivative is the area function of 2x. This, x squared, right, the antiderivative, is also the area function. So it turns out, at least in this example, that the antiderivative of the function that is the boundary of my area right here is that function's antiderivative. So the area function let's call that f of x, is the antiderivative. So in other words, if I take the derivative of f of x, I get g of x. So that's the big breakthrough. So if we know how to find antiderivatives, then we can find areas. So let's test that out on another function. So for example, if we had I didn't mean those to be red, oh well. Let's use, let's say 1, 2, 3 there. Let's use the same scale here. 1, 2, 3, 4. And let's look at the function y equals x squared. So this has points 1, 1, 2, 4, 3 9s off my graph, 1/2, 1/4. That would be down here. So here's my parabola. Oops, didn't come out very good. I start down here. So this is my g of x function. And I want to try and figure out what is the area underneath here at any value x. So I pick some x value there. I guess I can call this the x value over there. What is this area underneath there? That area is, we use in this fancy tall S there for the area. There's a reason for that you'll get to in the next class. I'm not going to worry about it right now. So we want to know what's the area with respect to x. So kind of like we divide by dx for derivatives, we multiply dx for antiderivatives, integrals. And in this case, I'm going to let x go from 0 over here up to some endpoint. So maybe that right there. Let's pick, that was supposed to be 2 there, wasn't it? So to 2 on that right there. I want to figure out what is that area. If I know an antiderivative, I can figure this out. So if g of x is the function, the antiderivative, I usually call that f of x, where f prime is equal to g of x. So I got to figure out what function could I take a derivative of to get x squared. So let's think about that. Derivative with respect to x of what equals x squared. All right, so we have a power rule that says we would drop the power by 1. So the power got dropped to 2, so that means over here, I should have had an x cubed. Now, if I take the derivative of x cubed, I get 3x squared. I just want x squared. So I need that 3 to go away. So then I'm going to divide this by 3. So if I take the derivative of 3x, I get 3x squared. And if it was divided by 3, like it is here, then the 3's would divide out, and I would get x squared as the antiderivative. So I think the antiderivative function for x squared should be x cubed over 3. Now, this function starts at 0, 0. That is important. If it started somewhere else, that would change the problem. We can look at that in a minute. But one thing to note here, then my claim would be that the area up to 2, that would be my x value, should be 2 cubed, or 8, over 3. So that area right there should be 8/3. And let's kind of play around with that idea to see if that's a reasonable answer. Is this really the area? If we were to draw a triangle here and say, well, the area is definitely less than this triangle right here. So that triangle right there would have a base of 2 and a height of 4. So the red triangle, like right there, would have an area of 1/2 times 2 times 4, which would be 4. Let's see, so what's 8/3? 3 goes into 8 how many times? 2 times, with 2 left over. So 2 2/3, almost 3. And so this green area is definitely less than 4, right? And it ought to be. We could improve our guess by making other triangles in here, or trying to find the area in slightly different ways. So I could say, well, let's make a couple of triangles. Let's make a triangle from, let's say, 0 to x equals 1. So find that blue triangle, and then I would have a square over here, and then I could make another triangle over there, right? So there are different ways to try and estimate that area there. And the more we break this up into little triangles and rectangles, like finding more points to isolate that area to try and hug this curve better, what we're going to find is we're going to get closer and closer to this 2/3 value. So I'm just going to do one more to double check that. If I try to break it down again in terms of, let's use blue here. Actually, it's erased just a little. It's not so messy. All right, so what if instead I went with a triangle from 0 to 1? That'll be a little bit above my parabola. My parabola looks kind of like that in there versus my blue line. So overestimate there with that triangle. And then next I have this square here, and then I would have another triangle up here. So these three, what do we got going on? The first one right here would be 1/2 of 1 times 1. And then the next one, that's just a 1 by 1 square. So plus 1 times 1 for that part. And then this one right here has a base of 1 there and a height of from 1 up to 4, a height of 3. So then I would have plus 1/2 times 1 times 3. So what does that give us? That gives us 1/2 plus 1 plus 3/2. We clean that up a little bit. That's 2/2. So we have 3, 4, 5, 6/2, or 3. So notice I'm closer to that 2/3 area. So the 4 was a big overestimate. There was a big gap when we did that one. And if we zoom in on the little the 2 triangles I made that are 1 by on the base, we'll see that we still have gaps going on there, but we're getting closer. So this idea of keep breaking this down into smaller and smaller chunks, then we start to hug the curve with these little lines, triangles, and squares and rectangles. We're going to get closer and closer and closer to that guy over there. That's kind of a preview of what's to come. For now, we're just going to play around with the idea of an antiderivative, which means can we look at a function and recognize what its derivative was from? So let's see. Give you a couple more examples. So the derivative, oops, again, the derivative of some function is equal to the negative sign of x. What is that function? Any takers on that one? Cosine of x, correct. Yeah, so remember the derivative of the cosine is the negative sign. All right, here's a harder one. The derivative with respect to x of -1 over x squared. Oh, shit. I did it wrong. The derivative of what function, there we go, is -1 over x squared. What function can we take the derivative of? What is this f of x here? Hint, if you're not sure, I could rewrite this blue function here as -1 times x to the -2. When we take a derivative of a power, oops, I got an extra x there. When we take a derivative of the power drops, so antiderivative of the power should increase. All right, so we have a guess. Guess is -x to the -1. And to check an antiderivative, you just take the derivative. So if I were to take the derivative of that function right there, you see the error there? You're close, right? The negative, yeah. So if I take the derivative of that, I would get negative times -1 x to the -2, and then that would be positive. I want it to be negative. Yeah, so it turns out we don't need that negative there, and then it works out okay. So it turns out the function I was looking for was 1 over x. Yeah, so I was hoping maybe you remembered the derivative of 1 over x is -1 over x squared. All right, let's try another one. So again, if it doesn't just come straight into your memory, then you got to kind of play around with the function, write something else down to help jog your memory to see what you recollect. The derivative of 1 over twice the square root of x. Oops, backwards again. The derivative of what function, f of x, is 1 over twice the square root of x. And because we're trying to jog our memory, we should always guess and check for these. There are other ways besides guessing, but at first there's a bit of memorization, just like we had to memorize formulas. So what function could this be? So if we're unsure, we could rewrite it. So how might I rewrite this? Well, I could think of the square root of x. Oh, we got an answer there. Square root of x, and then we check it by taking the derivative of that function. And hopefully remember its derivative is 1 over twice the square root of x. Alternatively, if that's something that's just not coming up in your memory, what I would do is rewrite this as 1 over 2 times x to the 1/2. And then that would be 1/2 times x to the -1/2. And then I think about, all right, if I took a derivative that reduces the power, so the antiderivative should increase the power. So then this is going to involve x to the 1 minus 1/2, increasing the power, add 1 to that. That would be x to the power 1/2. And if I take the derivative of this right here, that's supposed to be an arrow there, with respect to x, what do I get? Well, I get the 1/2 in front, drop that power by 1, -1/2. Yeah, that does match what I have right here. So square root of x is the candidate. So often we have more than one route to get to an antiderivative. Good job. All right, we're going to get harder still, medium hard next. The derivative of some function with respect to x is 1 over x. what function has a derivative of 1 over x? Natural log of x. Nice, yeah. Natural log of x, its derivative is 1 over x. Check. All right. Derivative of some function is 1 over x squared plus 1. Oh, and I wrote it wrong again. The derivative of some function is 1 over x squared plus 1. All right, so this one is a little more challenging. Quick question. Yeah, so the plus c I mentioned earlier, natural log of x is an antiderivative. Antiderivative. Another derivative, f of x could have been, switch to blue. That's not blue, it's blue. F of x could have been the natural log of x plus 17. Because if I take the derivative of the natural log of x plus 17, I get 1 over x plus 0, which is just 1 over x. So there's that idea I mentioned earlier. The problem with antiderivatives is that the derivative of a constant function is 0. So often when we take a derivative, we lose information. So reminder, when we take a derivative, we often lose information about the function. So if all I know is the derivative, I have a problem because the derivative with respect to x of any constant is 0. So I lost whether the original function had a constant or not. So this idea, so this is an antiderivative. So then I could say something like the general antiderivative of the 1 over x is the natural log of x plus some constant c. So it kind of depends how the problem was worded, what kind of answer is acceptable. This general antiderivative is also called an indefinite integral. So it's also known as, AKA, indefinite integral. So antiderivative and and integral go together. Indefinite means I just can't definitely tell you which function it is, okay? It could be the natural log of x, it could be the natural log of x plus 17, it could be the natural log of x minus pi. I can't definitely say it. So that's the indefinite. The only way you can end up with a specific antiderivative is if you know some information about a function. So to get a specific antiderivative, which is AKA also known as a definite integral, we need some specific information. Need more information. That information usually comes in one of two ways. One, a point on the original. So somebody would need to tell me that I have the point AB, or it might be stated as f of A equals B. If I know that, then I can figure out what the constant is. The other way I can nail and come up with a definite derivative is if it came from an area problem, then I need to know the start and end x value. Like that one I was looking at earlier for f of x, or let's call it, sorry, g of x equals x squared. I wanted to find the area from x equals 0 to x equals 2. So having those two x values allows me to get rid of the constants. Alternatively, having an x value and a y value allows me to figure out what the constant is. So that more information is either a point, or if it's an area problem we're working on with the antiderivative, we need to know where to start and where to end. And then we can get a definite answer instead of an indefinite one with that constant hanging out. So for example, based on the work I did on this one a minute ago, if this symbol right here is the indefinite integral, unless I get more information like start and end, so x squared with respect to x would be x cubed over 3 plus c. So that's the idea of an indefinite integral. Versus a definite integral would be integral x goes from 0 to 2 of x squared dx. And then the answer there would be the 2 first. So I have this antiderivative there. So I would have 2 cubed over 3 minus 0. Oops. 0 cubed over 3. So that's the idea of a definite integral. We use the indefinite integral. The constant's kind of irrelevant if we get this subtraction going on, or we can find the constant with a point. So we got a couple options there. All right, let's see. Let's go back a step. Yeah, we didn't get to that one yet. Let's see if we can guess at this one. So, and then we'll take a look at some homework problems. Derivative with respect to x of some function f of x is equal to 1 over x squared plus 1. What function did we take a derivative of and get that? Now, first guess would be it would be some other rational function. Hint, this one is not a rational function that has that derivative right there. Anybody remember which function has that as a derivative? It's not a rational function. Nice, Evan, arctangent, yep. The antiderivative here of 1 over x squared plus 1 is the arctangent. That's an antiderivative. Since I didn't say just find an antiderivative, I said antiderivative, I would say then plus c on the outside. Because when we take that derivative, we'll get 1 over x squared plus 1 plus 0, right? That constant goes away when we take the derivative. Okie doke. So a couple homework problems from here. Let's see what looks like fun. Antiderivative of polynomial, so undoing the power rule. Another one. Another one. All right, let's do this one first, and then we'll go back and look at polynomials in general. Screenshot. And here they're giving us some extra information. So we don't have to deal with a constant. So they're giving me a point. So then we're going to find an antiderivative for little f. So in other words, in this case here, there's this function big F that if I take its derivative with respect to t, then I should get the answer of 10, oops, secant t minus 8t squared. So thinking about derivative of secant squared, that sounds like the tangent to me. So the antiderivative, f, should have a tangent in it, because the derivative of the tangent is the secant squared. Now the 10, that's just hanging around. So derivative of 10 tangent of x is the secant squared. Minus, I'm just going to leave the 8 hanging out there for a minute, because the derivative of a constant multiple just carries along. Now the derivative of a power, the power drops, so an antiderivative, the power increases. So this should have a t cubed in it. Now when I take the derivative of t cubed, I get 3t squared. I don't see a 3 over there, so I'm going to compensate by dividing by 3. So, and then again, plus c in general. To check that that's an antiderivative, I just take the derivative of it. So before I use this information here, I'm just going to check. Am I making this up? Is it true? What is the derivative with respect to t of this function above? 10 tangent minus 8 t cubed over 3. All right, so derivative of 10 times tangent is 10 times secant squared. Oops, that should be a t. So that looks good so far. The minus 8/3, that's a constant multiple. I'm just going to carry that along. And then the derivative of t cubed is 3t squared. 3's divide out, leaving me negative 8t squared. Okay, so that does check. So I do have an antiderivative there. Next is to plug in the given information. If I plug in a 0, the answer should be 0. So f of 0 equals 0 means 10 tangent of 0 minus 8 0 cubed over 3 plus c is equal to 0. Cleaning that up a little bit, c is the only thing missing. Tangent of 0 is 0. 0 cubed is 0 times 8 is 0 divided by 3 is 0. So I get 0 minus 0 plus c is 0. So this tells me c has to be 0 also. So then the function I want would just be that simple antiderivative t minus 8t cubed over 3. Okay, so I needed that extra information to get rid of the c. All right, polynomials in general. A couple ways to think about it. So we looked already that the antiderivative, I'm going to use the integral symbol, of x squared with respect to x, that was x cubed over 3. If we wanted to find an antiderivative at plus c, for say x, that would be x to the first power dx. Well, that would have to be a square, increasing that by 1. If we take the derivative of x squared, we get 2x. This is missing the 2, so we divide by 2 to compensate. If I was taking the integral of x to the 5th, for example, an antiderivative for that would have to be a higher power, so x to the 6th power. But if we take the derivative of x to the 6th, we get 6x to the 5th. This is missing the 6 times. So over here, we divide by 6 to compensate. We always have that plus c. So in general, if you're looking for an antiderivative of x to the power n, then you increase that power by 1, and you divide by n plus 1, whatever that increased power is. So antiderivative for polynomial just hinges on this one right here, which is a tweak about power rule from earlier. All right, let's try another one. So this one right here, we have 2 derivatives going on, and notice they gave me 2 pieces of information there. So let's try this one. All right, so for this one right here, they're giving me the second derivative. So then the first derivative, f prime of x, should be equal to the antiderivative of that second derivative there. So 5x minus 1 with respect to x. All right, so applying the rules here, we get the antiderivative of x is x squared over 2, like we just played with. The 5 is still hanging out. Minus antiderivative of 1 is just x, and then there could have been a constant. So we don't know what that constant is. Is it 0? Is it something else? Double check that this is true. If you take the derivative of that right there, double check, that would be 5 times 2x over 2 minus 1 plus 0, which is 5x minus 1. So that does check. I do have the right derivative. So usually with antiderivatives, I check by taking the derivative because I'm more comfortable in that version over there. Now to figure out what the c is here, they give me this information here that f prime of 0 is 5. So if I apply that f prime of 0, which is what I calculated here, f prime, is 5, then I get 5 times 0 squared over 2 minus 0 plus c is equal to 5. So in this case, c is 5. All right, so now I know f prime of x. So I can definitively say out a constant f prime of x is equal to 5 halves x squared minus x plus 5. Now, I want to know what f of x is. So again, I need an antiderivative. So f of x will be the antiderivative of f prime. So then the 5 halves is just a constant. It's hanging out. Antiderivative of x squared, increase the power by 1, divide by that power. Minus, this is a power of 1, increase that power by 1, divide by the power. And this is just a constant right here, derivative of the constant, antiderivative of the constant, excuse me, would be 5 times x, and then we have the plus c. And then you should double check, if you take the derivative of this, will it really give you back what you started with? Okay, so the only thing I'm going to double check here is that if I take the derivative of 5x, I just get 5, right? And then they give us more information that to figure out what c is, f of 0 is 4. So now I can find what the value of c is. So if we plug in a 0 there, let's call that 5 over 6, 0 cubed minus 0 squared over 2 plus 5 times 0 plus c equals 4. Those are all zeros, so this tells me c equals 4. So now I've nailed f of x. So f of x, is equal to 5, 6, x cubed minus x squared over 2 plus 5x plus 4. Now in the last few examples, the constant was the y value. That won't always be the case, right? So don't just assume that that y value is the constant. You got to run through and check to see what c is by plugging in the given x value. And then the final question here was, what is f of 2? So now I have enough information to plug in there and figure out what f of 2 is. And I'm confident that you guys can do that. All right, so antiderivatives. This is a good review of trying to remember what our derivatives are. So anytime you take an antiderivative, for a while now, I highly recommend you take its derivative to see if it does give you back the function you started with. Can you go both directions? Important. Okay, other things to look at. Let's talk about the final exam. So the final exam is cumulative. It's going to cover everything. It's mostly going to cover chapter 4. So the exam is going to be about 3/4 about chapter 4, and then there'll be a question or two from chapter 3 and chapter 2. So in general, and I set up a practice final. The practice final is optional. You don't have to do it, but it's strongly recommended. And I believe I have a couple of sample finals posted there. Kind of an overview. Yes and no. So it's going to be kind of like the first exam where it's going to be, the questions will be online, like the homework, and you just get one try on them, and then there'll be a place for you to submit your written work. So more like the first exam was. And yes, it will be timed. So I'm going to set up the exam to be finished. You should be able to finish it in under an hour, and then I will give you 3 hours to get it done. And you have Monday through Wednesday to do so. And I'll send out an announcement about that. So kind of overview, there will be a couple questions on basic limits. How many questions are on it? I'm still writing it. Usually final exam is about 50% longer than a midterm exam for a class like this. So if a midterm exam had 10 questions, then this final will have like 12 to 15 questions. And again, if you're well prepared, you should be able to finish it in under an hour or in an hour. And then you get a little more time just to make sure. And it'll be set up so that after you submit it, you can submit your work. So there's no time limit on submitting the work, like the time limit for submitting the answers. But I do expect your work to come within like 15 minutes of taking the exam. As far as the weighting, it's in the syllabus. So if you check out the syllabus, the final exam is worth about 20% of your grade. So each exam was 20% of your grade. The final is another 20%. Homework was 40% of your grade. Good questions. So basic limits, we've used those again and again, and then we have some enhancements to limits like L'Hopital's rule, which is kind of cool. And then the basic definition of the derivative, you should still be able to do that. Derivative. So this is chapter 2 stuff that'll be on there. Chapter 3 was mostly just derivative rules. So there'll be a couple questions about that. And the problem with just testing you on derivative rules is you have access to the book and you have access to things like the derivative calculator. So me just saying, hey, what's the derivative of the sine of x? That's not really a worthy question. So as far as chapter 3 goes with our derivative rules, what I would normally ask is I would have like a no calculator version of the test, and I'd say, okay, here's a bunch of functions. Tell me what their derivatives are without using something like a book to look them up in or otherwise, but I don't really have control over that. So as far as derivative rules, the main things I expect you to show me work on are the harder ones, like the quotient rule and the chain rule. Otherwise, most of the other derivatives that we take are pretty memorized. And on this kind of test where you have kind of infinite resources, there's no point in asking those. So there'll be a couple of questions about quotient rule, chain rule. Other big things from chapter 3 were implicit differentiation. You can expect to see that. And what was the other big idea from chapter 3? With implicit differentiation, we had that idea of logarithmic differentiation. And then applications from chapter 3, which were rates of change. Then chapter 4 was just further applications of derivatives. And I can't ask questions about all of them, there's just too much stuff there. And so it'll be a selection, and the big ones there were related rates, and then shapes of graphs, the shapes of graphs led to those max and min problems. And those were often called, when they're applied, optimization. So max and min problems, optimization. And other applications that came up besides the optimization and related rates would be Newton's method for finding roots. And so the sample, the practice problems I put up for the final, there's 60 questions that cover this stuff. I wouldn't give you a 60 question one. So I would expect to see one question about basic limits, one question about the limit definition of the derivative, one or two questions about derivative rules like quotient and chain rule, at least one question about implicit differentiation, maybe a logarithmic differentiation problem, definitely a rate of change problem. So an application like growth of a bacteria culture, or what else do we look at? Marginal profit, for example. So there'll be something like that. Definitely going to be a related rate problem on there, an optimization problem, and then a question about shapes of graphs for sure. Most likely a question about Newton's method. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 questions minimum that are going to end up being on the exam. And I don't like writing really long finals, so it won't be too long. I don't think I'm going to put antiderivatives on the final. Sometimes I do, sometimes I don't. I'm mainly, that's kind of like an introduction to what's next. So I don't think I'm going to put an antiderivative problem on there. So I'm just going to say probably not, but I'm not. Probably not. That's a good question. Antiderivative. Okay. I have office hours tomorrow at 10 o'clock, and if you need help with something else, then there's always that message instructor button attached to each problem. So feel free to hit that over the weekend. I'll get back to you, and then I will post more information about the final exam. Yes, I'm going to give a 3-hour time limit, just because, again, if I expect you to be prepared, it should take about an hour, but weird shit happens in the days of COVID. Cole, you definitely better find a stable internet connection for this one. You don't want to get kicked out during the test. You will be able to get back in, by the way. So if somehow you get kicked out of the test, you'll just be able to get right back in and pick up where you left off. It's going to save your work automatically. So I did have that set up just in case we have any internet or power glitches. And if you do, again, have a serious internet or power outage, Cole, give me a call. When I post the instructions, I'll make sure I put my cell phone number on there in case you have any emergency problem while you're taking it, so I can help you resolve that. All right, thank you for doing calculus with me this term. You guys are awesome. Study hard, get some good sleep in between. Okay, let's see. If somehow, like internet issues, will so that's the problem. The time doesn't stop. It's once the exam is started, the timer is functioning. We're on some Amazon web server where it lives, so it keeps ticking. So that's one reason I'm going to give you my cell phone number so you can get in touch with me immediately. Now, I get a lot of junk calls on my phone. So if I don't answer at first, it could be because I don't recognize your number. Leave a message and I will check. If it rings and then there's a message, I will get right back to you. So if I don't answer immediately, definitely leave a message if you have a problem. So you just have to decide sometime between Monday and Wednesday when you want to take the final. You want to make sure you have a clean, clear window of time where you're interruption-free, you're well-rested, well-fed, your notes are in order, and you're ready to kick butt on math. So be sure you get yourself in a good place to do that. Okay, you're welcome. It was a pleasure working with you all. And you're going to have fun with Mr. Hermberg next quarter in Calc 2. That's some wicked cool stuff also. So have a great day, do good math, stay in touch. I will see you soon. Bye-bye.